Good morning, everybody, and welcome to the G2M Research Multi-Vendor Webinar on Computational Storage and Use Cases for Computational Storage. Our webinar today is sponsored by Ditacom, Samsung, NGD Systems, and ScaleFlux. Let me go over some of the agenda and ground rules. So one thing is that I'll do a little bit of an intro at the beginning to introduce the topic. Then each of the vendors will speak for about 6 minutes about their technology. We'll then go into 3 key questions we will ask the panelists, and they'll each get a couple minutes to answer the question. And then we'll also have 3 audience surveys interspersed between the key questions where we're going to ask you questions, and you can answer using the Zoom controls. And at the end, we'll do a Q&A for about 13 minutes. So when you want to do Q&A, please submit your questions through the Q&A window, and then we'll answer them live. And we'll wrap up about 10:20 or so. About 2 days from now, everybody who is registered for the webinar will get a link to the webinar recording, as well as a set of the slides that are presented here today. So with that, let's go ahead and jump in. My name is Mike Human. I'm the managing partner of G2M Research. Joining us today from Samsung is Pankaj Mehra. He's VP of Product Planning Team at Samsung. J.B. Baker, Senior Director of Product Management at ScaleFlux, Stephen Bates, who's the CTO at Ditacom, and Scott Shadley, who's the VP of Marketing at NGD Systems. So kind of starting out, what is computational storage? What does that term mean? And it means a lot of different things, and we've got a few SNIA slides in here as well to help define it also. So this is not just my view of it, it's kind of the way that people are looking at today. But it's really, in the end, it's a means to accelerate application execution for data sets and problems that have very large data sets by co-locating the processing capability with the data storage. You can think of it as an extension or kind of a miniaturization of the concept of data locality, which was really started by Hadoop with MapReduce, where they started moving processing to where the data resided rather than vice versa. And one of the big drivers of this has been the fact that we're looking at data sets now that are really petabyte scale for a large number of problems, many of which are real time and many of which are deployed or edge computing centric. So with all that, the real goals of computational storage, and there's about 4 of them, are number 1, to reduce the time it takes to perform those petabyte scale computations. In other words, how can we make these things more real time if they're not real time today? Secondly, reduce the energy and cooling for doing petabyte scale analytics. If you think of petabyte scale systems today, you think of large clusters, lots of power, lots of cooling, lots of footprint, right? And lots of cost. So one of the goals of computational storage is to reduce both of those sets of criteria so that now you have a technology that can be used across a larger number of problems. And then finally, and this is an important one, allow processor power to scale linearly with the size of the problem's data set. One of the problems we've always had with standard computational approaches is that you scale the two, basically, they're kind of in sync, and if you don't get them right, it's a problem. You can either have too much computational power or not enough computational power for the size of the data set or vice versa. And one of the goals of computational storage is to get rid of that problem. For those of us who have been around, it's interesting because we always see the same things happen over and over again. And computational storage is kind of like that. It's gotten smaller and more powerful, right? So if you look at it, the whole idea of putting storage with processors or vice versa, putting processors with storage, really started with some of the massively parallel processors that were done in the HPC world. The Goodyear MPP, which very few people have probably heard of, it was a multi-thousand node system that had storage co-located with each of the processors. In 1983 was one of the first examples of this. Something that more people have probably heard of, the EMC Cetera, was a content addressable storage. Not exactly the same thing as computational storage, but a lot of the same attributes to it. IBM also had a system called the DR550, which did similar things as well. And that you think about it, computational storage really, it's not a concept that says it has to be in a drive. It could be done at the chip level, it could be done in the storage device. system, memory, or potentially many other levels. So there's a lot of potential ways of implementing this. Some of the challenges that we've heard people talk about around computational storage market acceptance include having to modify applications. If you had to change an application for a specific capability or specific technology, oftentimes that can be a barrier to adoption. Go-to-market channel adoption, are people going to be able to buy these from standard IT sources? As we all know, getting buyers to change the way they want to buy technology is always a challenge. So having it available through the standard SIs, resellers, and OEMs is, important. Crossing the chasm, you'd be reticent to not mention that with any new technology. Most IT buyers want to see a technology be adopted by others like them, so to speak, in the mainstream market before they adopt it themselves. It's a risk approach. As we all know, IT buyers tend to be very risk averse. And finally, standardization. Do standards exist for this technology so that you can avoid, the problems of vendor lock-in or things like that? On that last point, one of the things that SNIA recently did, and we've got one of the SNIA co-chairs, Scott Shadley, with us for the SNIA Computational Storage Technical Working Group, but they actually formed a working group to work on interoperability between computational storage devices. It was founded in October of last year, has 40+ companies that are participating with a lot of members, over 100, all trying to work on coming up with ways of putting together computational storage and standardizing so these devices can work together and hopefully eliminate that last bullet as a problem to adoption. And with that, so last thing, SNIA and the TWG define basically 4 computational storage categories. The first one being computational storage devices. This would be an actual device like or a controller that could provide computational storage capabilities. Computational storage drives, think of that as an SSD, or I suppose a hard disk if you really wanted to go old school, that has also computational storage capabilities in it. Computational storage processor could be co-located with another part of the system to actually provide those capabilities. And then finally, a computational storage array, which provides multiple combinations of these things together to provide the capabilities that you're looking for in computational storage. So with that, let me pass it over to Pankaj from Samsung. He's going to go through his part. Okay, Pankaj, you should have control now.
Hello and welcome everyone. I'm Pankaj Mehra. Like Mike said, I'm with Samsung Electronics in Device Solutions America, and I lead the product planning for Smart SSD. So let me kick things off from our perspective. Actually, Samsung's been working on storage smarts for over 8 years. Our first papers are from 6 years ago when we published database conference papers about intelligent in-storage compute. I myself have some history at Tandem Computers, where in the 1990s we were developing disks that could run database executors. These were called XIDs, which is executor in DP2, for those of you who know. The idea, whether it is active disks work at Minnesota or XID at Tandem, it's an old idea which goes like this, that when you have very large scale data, and that depends on which generation of storage you're talking about, it's better to move, it's better not to move that data outside, because at accelerators and at CPUs, a kind of funneling happen when many devices are trying to send data to the same computer. Instead, it's better to move to local compute, whether it's for sorts, joins, partial group buys, etc. And so on the right of this picture, you see that when you do that, meaning you place an accelerator right next to a SSD controller and flash memory, good things happen as shown in green on the PCI bus, which is there is minimum data movement, which reduces CPU load. This idea is called offload. Near data processing happen, which Mike said it's basically basic idea of locality, which also gives you the ability to scale. And then scaling benefits from the concurrency of multiple devices and parallelism that results. Also, if you create this kind of local data paths, your net bandwidth goes up. Okay. So to prove out these concepts in the latest generation, after my arrival at Samsung in 2017, we engineered our first product, largely, a board level integration of a traditional SSD with all its controller parts, with a Xilinx FPGA and intervening DRAM that you can see on the left side. And then we ran some industry workloads to see if the ideas actually do prove out. This work was done by us in 2018 on our first generation POC, which is a half-height, half-length add-in card, AIC as it says here. We are also working on newer devices. I'll show that in later slides. But what's interesting on the right-hand side is we started working with customers very early. We had been working with a financial industry customer, which is a large hedge fund, who like to calculate custom pricing formulas on historical data from the stock market, for example, for portfolio-backed pricing calculations. So there, what we noticed was that when we introduced the Smart SSD into the mix, we see a 3x increase in performance with constant CPU utilization. So without overwhelming the CPU, you can actually drive up how many millions of operations you can do, pricing operations you can do against large amounts of stored stock price and volume data, such as comes in over stock exchange formats. On the top right, you see us running a very traditional TPCH analytics benchmark on a homegrown MySQL variant called MariaDB with a homegrown extra DB storage engine. And across the 22 queries in the benchmark, we saw a 3.5x acceleration. Some scan-heavy queries were accelerated more than 100 times when we ran this benchmark. So at the bottom, number 3 is shown, which is we took industry data about flight arrival times, scheduled and actual, and we ran queries that tested whether the flights took off late and where the problems were most acute. In these benchmarks, with the introduction of the first smart SSD, we saw 4x improvement. And then as we doubled the number of smart devices, we saw approximate doubling in performance. Trying to advance this slide. Okay. So the basic idea that we've been putting forth is that such database operations, as were shown on the previous slide, that result in net reduction in the amount of data that is to be communicated, benefit from moving into local compute near the storage. And so examples of these are scan filter operations, such as are generated by Spark query plans, aggregates, which exist in both MapReduce operations and database in general, like if you're calculating min-max average or any other statistical moment, etc. So these tasks can execute concurrently, locally, and without the accelerator funneling, and represented a set of tasks in a typical pipeline is shown here. These days, the data at rest might be Parquet format. The hosts like to talk to intelligent devices, just like they try to talk to any other cluster node. And arrow format could be the way that you return results to the host. Okay. If we move quickly to the next slide, a different kind of use case is shown here. Here, what we are seeing is storage nodes and common storage tasks such as compression, decompression, encryption, decryption, dedupe, and actually very importantly for infrastructure as a service, I/O for virtual machines. All these tasks that benefit from executing near the device rather than outside the device. For example, in decompression, you can get both QoS and latency benefits in addition to throughput benefits. And when you do I/O for virtual machines, instead of wasting costly x86 cycles that you could monetize for dollars, you end up running the hypervisor-like functions, virtualization functions, in the device itself. Okay. So as promised, here is the quick view of the Samsung roadmap. So beyond the add-in card, like I was saying, at the top of this picture is shown our U.2 device that we are working on right now. We expect to have engineering samples within a few weeks, and then we are making the device available to partners and customers in the third quarter of this year. And our goal here is to go beyond showing scaling on 4 devices, such as we have been doing with add-in cards, to showing scaling with 24 or 48 devices and really prove out the concept of more bandwidth by showing greater integration. So we are working on faster internal data paths as well as other optimizations. Let me pass control back to the moderator so we can keep moving. Thank you.
Thank you, Pankaj. That was really, really great. Let me jump quick. I guess I got a couple more slides. So let me jump to JD. JD, if you want to go ahead, I'm going to give you control.
Okay. Thank you, Mike. So I'm JV Baker. I run product management for ScaleFlux, and we're not. There we go. So you might not have heard of us as much as you heard of Samsung before, but so ScaleFlux has been a recognized leader in computational storage. We've won multiple awards since being founded in 2014. We're in production with our computational storage drives, or CSDs. These combine the high performance, low latency flash storage of a PCIe SSD with integrated compute engines, or the computational storage processor capability, into a single device that plugs into industry standard servers. These are in U.2 and half height, half length add-in card form factors with capacities up to 8 terabytes today. We're headquartered here in San Jose, and we also have development or really test and qualification teams in China. We're seeing, we've deployed in at least these 5 applications, more applications coming to customers. So, across Aerospike, MySQL, OpenZFS, Hadoop with MapReduce, and Apache HBase, we've been able to have our customers see significant improvements in their system and application performance. I don't have time to go through all of those today, so I'm just going to hit 3 of them. First here, Hadoop, where we're offloading the compression and erasure coding. And the benchmark we use here is TeraGen and TeraSort. So first we run the TeraGen, we run the benchmarks with an HDD only array of 9 nodes set up with a 6+3 erasure coding. And then secondly, we run the benchmarks again, adding a single ScaleFlux computational storage drive to each of the servers. So with TeraGen, we're creating 1 terabyte of 100-byte database records. We then compress them and run erasure coding before storing all this data out to the disk in the cluster. By offloading the erasure coding and compression to the CSD, we reduce the job runtime significantly down from 405 down to 155 seconds, translating to 260% job throughput. TeraSort is the second part of the test, where TeraSort reads back in all the data, sorts the records into order, rewrites the sorted results back to the Hadoop file system, again compressing and erasure coding the data. Here, by offloading the compression and erasure coding and utilizing the flash in the storage device for temp storage, we see a 34% reduction in job runtime, again translating to almost a 50% increase, or just over a 50% increase in throughput. Now, when magic happens when you put both of these together, with using the ScaleFlux drive, we net over a 60% increase in total job throughput. And then as we ran that through and calculated TCO and including how much it costs to add in the ScaleFlux drive and then the power for running these things for 3 years, we saw a significant reduction in cost per job and TCO, over a 30% reduction over those 3 years. In the second example here, really got to look at these 2 graphs together. And so we're running HBase with the YCSB benchmark. And again, we're offloading the compression function and utilizing here CSD for the flash for a bucket cache. So looking at these two graphs together, on the left, you've got the, you see that offloaded compression achieves basically the same through total compression as a host-based compression. And then in the middle, you see that by doing the offloaded compression, we get over 2.5 times the throughput of host-based gzip compression. So when we combine the two together, you basically get 2.5 times the performance with versus a host-based compression, or you get very similar performance while getting take advantage of, or very similar performance to no compression while getting the benefits in cost savings of having the compression. In the right-hand graph here, we're looking at the benefits of using Flash for bucket cache in a heavy read environment. Here it's 95% reads. And regardless of the scenario, you can see that using Flash bucket cache does a massive improvement in performance over a hard drive only system. With writes as only a very, very small portion of this workload, the total performance is similar for both the offload and the CPU-based compression. But as you increase the percent of writes, then the benefits of offloading the compression start to come out and shine. And the last one here, OpenZFS. So in this graph, what we're doing is comparing different ways of different compression options. So the red line is the baseline of you're doing no compression, just running in the ZFS. But assuming you'd like to do some kind of compression to save on your storage cost and space, there's 3 options that we looked at here. So first, you've got LZ4, which yields throughput at close to that no compression level, and that's that yellow or orange line, depending on your screen. Second, you've got the host-based gzip, which is that bluish gray line at the bottom that chugs along at only about 400 megabytes per second. And third, we'd have the gzip offload, which steadily climbs with record size. So the larger the record size, the more compression we're able to get, and the further it stands away from gzip compression, host-based gzip compression. Well, all these options are very close when you've got small record sizes. You can see that it spreads out as the record size increases. And while it should be pretty clear that offloading the gzip gives you significantly higher performance than doing host-based gzip, you might wonder, well, why bother with that gzip instead of just running LZ4 when LZ4 has more throughput? And that comes down to the storage cost. So the gzip is a more efficient compressor engine than LZ4. So on your storage cost side, you save an additional 23% of the storage space when doing gzip versus LZ4. So it's not up for everyone in this case, but if you need the gzip level compression, offloading definitely increases performance versus CPU, and it saves you money over LZ4. And that was what I have, so I'll pass back to Mike.
Thank you very much. That was a great view of some different use cases for that. Jumping to Stephen Bates, Stephen, CTO from Idedicom. Stephen, I'm going to pass you control.
Great. Thank you, Mike. Can everyone hear me?
There you go.
Can you hear me, Mike?
Perfect.
Excellent.
Perfectly.
Afternoon, everyone, from a lovely day in Ireland. My name's Steve Bates. I'm the CTO of a startup in the computational storage space called Idedicom. We're a team that came from enterprise storage, ASICs with PMC Sierra, and we've got a rich history in both enterprise storage and NVM Express, which ties in very nicely to what I want to talk about today. So, Pankaj and JB both spoke about the products that they're offering, and I'm trying to go to the next slide, Mike, but I can't seem to be able to. There we go. Sorry about that. What Idedicom is doing is we're also doing computational storage, but we're focusing on a different product category, and this is something Mike touched on earlier. SNIA are developing terms for a range of different products that vendors are expected to offer in the computational storage space. Both Pankaj and JB were discussing the computational storage drive, where processing is added to a solid state drive. Adedicom is focused on a slightly different product category within computational storage, and that's the computational storage processor, or CSP. And this is a component that provides computational storage services without providing the persistent storage. And I think there's going to be solution spaces where CSDs are desirable, but there's also going to be solution spaces where CSPs or computational storage processors are desirable as well. And so it'll be interesting to see, the pros and cons of those product groups as we go forward. And I'll dig into that a little more in the next couple of slides. So one of the things that Adedicom identified pretty early on in our existence is, in order to make these computational services consumable by operating systems and by applications, we needed some kind of standards-based paradigm, standards-based framework to go do this work. And Adedicom is very heavily invested in NVM Express for computational storage. So I think most of the people on this call are familiar with NVMe. It's an incredibly successful protocol for talking to next generation storage. And several people have noticed that NVMe itself is actually a very, very good transport and can be used for things above and beyond pure storage. And in fact, I recently gave a talk at NVMe Developers Day discussing how we can extend NVMe for computation. And Mike put up a slide with a lot of company logos on it. And that's standards work that's being done within SNIA and NVM Express. And there is a momentum to bringing some standards to bear around deploying computational storage devices through NVMe. The products that we build are all NVMe compliant. And we provide computational storage services, whether those are storage services like compression, encryption, and so forth, or whether they're more analytic-based accelerators like AI and regular expression matching behind an NVMe controller framework and inside a NVMe software-based ecosystem. So that said, we do have a range of products that we're currently shipping, these computational storage processors. And what we've seen is very interesting is some of our customers are very keen to consume us in different form factors. So some of our customers are very keen to consume us in a storage form factor. And for those customers, we typically deploy in something like a U.2, which is very much like a classical NVMe SSD form factor. Pankaj showed you a diagram of their smart SSD moving to that form factor, and we already have shipping product in a similar form factor. The great thing about this form factor is there's a lot of 2U and 1U servers now that can accept multiple of these. And because our performance scales, the more of these devices we add, we get a nice scaling kind of benefit from these storage-centric form factors. In addition to that, though, we can deploy on more classic accelerator form factors like add-in cards, such as the one based on the new Xilinx Alveo that you see in the bottom of this slide. So some customers would like the storage form factor, some would like a more classic accelerator form factor, and the great thing about our technology is it can deploy equally well on both of those. I do want to just spend a second talking about the software stack. For us, certainly for me, software is an incredibly important part of making this all work. If we can't make accelerators and computational storage services consumable, then they are not going to get mass adoption. And so we've been very, very cognizant of the fact that any software stack we deploy has to have very little impact on things like operating systems. And in fact, we can deploy using the standard NVMe drivers that are available in your favorite operating systems today. And we also need to be aware that any changes have to occur in user space need to be done in a kind of vendor neutral based way. And again, NVMe is the mechanism by which that can be done. So the way we typically deploy today from a software perspective is using standard NVMe drivers in the operating systems, and then providing user space libraries that tie into applications. And you know, that's a really important part of all of this story. The hardware is exciting and it's good, but without good software and good manageability, the ability to deploy this, the ability for our customers and our customers' customers to consume computational storage is very limited. So the software story is very important. I do want to dig into a couple of specific use cases. So we have a solution right now that takes our computational storage processor and our software stack and ties into the production key value storage engine RocksDB, which is deployed at places like Facebook and others. And we demonstrated this work at OCP, but we combine our computational storage processor with NVMe drives from any vendor, because we don't actually have the storage. This allows the customer to pick their favorite NVMe provider, whether that's Samsung or Intel or WD or someone else. And we can combine those to provide the solution. We got this engine store running 6 times more transactions per second. That's a very important figure of merit for someone like Facebook. How many transactions per second per server? We were 2.5 times more efficient on the central processing unit. So we were doing over twice as much work as you could normally do in one of these servers. And we actually reduced the NAND costs of this system by a factor of 4. So all of those add up to a much more efficient RocksDB deployment, both in terms of capital expenditure, how much do I have to spend to get this system off the ground, and also the operating expenditure, how much do I have to spend to keep this system running 24/7, you know, every day of the year. In this particular instance, the customer was looking for that classic form factor, so we deployed on a Xilinx Alveo card. But in other cases, other form factors are more interesting. And like I said, this was with our software stack, but tied into the NVMe ecosystem. So using the NVMe driver that's provided in the major operating systems. Another example is actually similar to one JB discussed. This is compression offload in ZFS. ZFS is a very, very popular production grade file system. The advantage of providing compression in a file system is it doesn't really matter what application runs on top. It gets the benefit of that compression offload. So you can run your database on top of ZFS or some kind of analytics or AI, and that would get the benefit. We actually, in this particular customer example, deployed on our U.2 form factor. So we have our Adedicom computational storage processors in U.2 form factor, again, combined with a number of SSDs. In this case, the SSDs were OEM'd from Dell. And in this case, we actually achieved 26 times improvement on the CPU load. So a really significant offload in terms of how much we could offload the processor. And that's very important for something like this, because any of the CPU offload that you achieve with computational storage is more CPU that's available for your application. So very, very important to get that offload. On top of that, you also get reduced data movement and a more efficient system. So that's another example of where we're deploying our computational storage processor. And again, tying into that NVMe ecosystem just helps to make all of this much more consumable, which I think is going to be very important in order to get mass adoption. So I will hand control back to Mike.
Thank you very much, Stephen. And last presenter will be Scott Shadley of NGD Systems. Scott, you should have control at this point.
Good morning, everyone. Glad to be a part of the session as well. Thank you for sticking with us, since we have quite a few presenters and a bunch of time to cover. So from our point of view, if I can get it the slide forward as well, there we go. NGD Systems, now it's going too far, too fast. Let's get it back to the first page. All right, so we've also been in this landscape since 2013. So this is our 6th year in process of developing these particular solutions. We're the first ones to have deployed into production environments, the NVMe variant of the computational storage products. So as mentioned by Steve, NVMe has proven to be the best choice, if you will, from a protocol and standpoint perspective. We took a slightly different bent towards how we're doing what we classify a computational storage drive, and we've built it as a turnkey SSD. So what we've done is it's an off-the-shelf NVMe storage device, or can be used as an off-the-shelf NVMe storage device, and the compute resources that we offer, or the computational storage services that we offer, are actually available to be turned on or off based on the needs of the customer's platform or development. As we started thinking about that as well, when you start looking at the storage environment that we're in today, the genesis of computational storage, as Mike talked to at the beginning, is very important, but realistically what's coming into the proof point of why we need all of these really innovative solutions is the fact that the amount of data we're generating is becoming very large, and the ability to manage that data becomes challenging. So we've also focused on building very large capacity capable drives. And all of this is built on an ASIC-based solution. So all of the preceding products today are FPGA-based, which has a lot of opportunity and advantages for each of those solutions. We looked at it from an ability to get into, again, where we are talking about customer-friendly form factors. And so in order to get into things like the M.2 form factor, or a larger capacity U.2 form factor, or even the EDSFF as it becomes more popular, you needed to be able to have access to that larger scale, lower power envelopes, and an overall better TCO for the cost of that particular solution. So when we look at it, we've built a programmable computational storage service, computational storage drive. Since I'm the co-chair of the working group, you get all the acronyms from me, but I did spell them out there for you. And we looked at it from a perspective, you take a standard drive and you move the compute into the single ASIC solution, and you build a workable stack out of that. And so from our perspective, it needs to be simple. As Stephen mentioned, as part of the growth of the market, you need to have a standard protocol, so everything's NVMe based. No fancy extras required to communicate with the device. It just talks over the protocol. Minimize the data movement. So having single chip solutions means you're having even less delays of light speed, if you will, going from an FPGA to a controller, or from an FPGA to another device. And of course, making sure that as you do this, you provide a better overall customer TCO. And so our API platform sits on the host solution. It transports all of the compute requirements and computational capabilities over that traditional NVMe protocol. So if you look at it from a hardware and software perspective, on the hardware side, you can see I built a fun little block diagram. And since I'm a marketing guy, I had to do a little more creative than just simple blocks, because that's way too easy. So you can see that on the host side, you have your desired application that's handed off to the NGD host API. We transport and use the transport protocol TCP to go over the NVMe protocol to the drives. So there's been a very large movement in the NVMe over fabric space to do TCP, or NVMe over TCP. So we've already done it, but kind of in the reverse. So by nature of that, you can think about the fact that we're also very fabric friendly with our devices, and the ability to transport our computational resources still over those protocols, and eventually, if you will, become TCP/IP direct. We use a quad-core ARM processor in our solution, which has a running Linux OS platform on it, where we actually migrate that host app into each and every individual drive, and then we treat it like a traditional storage product. So you can see the NVMe talks to the media controller, and our NAND device, the NAND devices on the drive can also be talked to directly by the OS that's running the application. So it's kind of a capability to have the best of both worlds from a storage product and a application accelerator. So on the right-hand side here, you can see kind of a software block diagram of how we've assembled the platform. The blue box represents the Newport controller, or our ASIC solution. And within that, what we classify as our in-situ processing engine resides within the green box inside of that. So you can see they are integrated in separate type of applications to be able to manage all of the user space data and information, as well as have all of the flash control. And since we did decide to build a traditional flash storage device as part of this overall solution, we decided to be very aggressive with the amount of media management capabilities. So our ASIC solution is a full 16-channel NVMe SSD controller that also happens to embed this capability of compute and application acceleration. So you'll get a copy of these slides so you can review these in a little more detail as you like. The API that we do run on the host is NGD specific today. We do realize that when it comes to customer specific use models, it becomes more challenging for industry adoption, hence why we were one of the founding members along with all of the other members on this particular webinar to develop a more generic or customer agnostic or vendor agnostic customer friendly API platform. So if you think about the different ways that we can deploy this, we've got multiple form factors of drives shown bottom left, but really what it's about from this perspective is what we can do with the compute capability. So we've highlighted the ability to run TensorFlow on the drive. In this case, the current example is image classification, being able to drop files onto the drive and have them auto sort into different classification folders. And by doing so, we've been able to show greater than 10x value improvement from that perspective. We also note that the idea of running containers is very popular right now. So we've got, because the drive has the capability of running a Ubuntu OS on the drive, it's also natively able to support Docker containers. And we've been able to literally go out to the Docker store, download an API or application from the Docker store, drop it into the drive and execute in place real time on the drive. We've had some fun with facial recognition, license plate recognition, things like that. It's becoming very popular with our IoT customers. There's a recent deployment in China where they're using AI and containerized apps to do license plate recognition to auto bill you for parking so you don't have to use meters or apps. And that's a good use case for that. And then we've been continuing to optimize the Facebook artificial intelligence similarity search, which is shown top right. That's a joint project with our friends at Microsoft that's been ongoing for the last year and a half and is getting closer to deployment. Right now, it's showing a 500x improvement in the ability to do that image similarity search. And then lastly, I kind of skipped over the Hadoop workload. I wanted to kind of spend a little bit of time on that. I know JB was kind enough to show his version of that particular solution. This is a way for us to highlight the multiple different paths to improved analytics and improved use of a different workload by the different solutions that are available from us as vendors. So if you look at a traditional Hadoop platform, you've got your data nodes, your name nodes, and you've got your CPU that's running all of these different product solutions. In our case, the test that we ran used the Terasort and word count applications, and we looked at it from a perspective of full court drive replacement. So we know that today everybody's loading them with lots of hard drives, and you need to be able to throw in some accelerators and other drives in alongside those solutions. But what if we could actually replace the entire storage contents because flash storage is getting so cheap at this point in time? And what can we do with that? So if you look at the graphs on the right, running it as a traditional Hadoop workload, the response time is generic. It's always flat no matter how many drives you have, which is kind of the concept behind Hadoop, is you always get consistent results regardless of how dense the platform is. And we stopped in this case at 8 drives because we have a partner in Europe that does online reservations for hotels and airlines and whatnot, and they have a power envelope problem where they can only put 8 drives per server. We are continuing this experiment and we can provide future results on it as well. So what we did in this case is we actually migrated the data nodes into each and every drive. So we did all 8 drives, moved the data node into our in situ processing processor in our Newport controller. And you can see up top that we had some results that, if you will, came out higher. And that's because if you think about it, the original platform used 16 cores on that single processor to generate those results. We looked at it from a TCO perspective and said, how can we make things better, faster, cheaper? So we reduced the core count on the system because we know in the case of most situations, 8 drives is never enough for Hadoop clusters. And so we cut the core count in half, freeing up the CPU to go do other things, move the data node into the drive, and you can see at 4 drives, we now are equivalent in processing what 16 cores could do on the traditional platform, and we continue to improve to roughly 40% faster in the results for both of these drives. Now, if we think about it from just a sheer performance perspective, a 40% improvement's great. People will start to give you the throw out that, well, okay, you're replacing hard drives with SSDs, so your TCO can't possibly be better. But then if you look at the actual platform development, and you see that if you take and want to build using the current 8 terabyte SAS drives that are available on the market in a 12U 2U server, at 9 nodes, you have 864 terabytes in a total of 9 cores that can do data processing, 1 core per server, because we kept it at a single node, trying to keep the cost down. If you look at the availability with our M.2 platform, since we have an ASIC-based solution, we take that 18 U's down to 3. So instead of 9 2U servers, we have 3 1U servers. We're using a partner's 36 drive, 8 terabytes per drive. And because each of those drives has a quad-core processor, and we're offering those cores to be able to process the data, you go from 9 cores of processing to 432 cores of available processing in 1/3 the space. So in less than 1/3 the space. So you can see there's a substantial advantage to the capabilities that computational storage drives can offer, both from looking at it as a storage device as well as the processing. Going to 432 cores of available processing, if we were to, as we develop the final solution on a fully populated node platform, you'll see those results can continue to improve to even beyond the 40% mark today. So if we go back to kind of highlight where we stand with the concepts on this Microsoft project that we've been building out and developing, you can see it comes down to not only the speed at which we can accomplish things, because we continue to look at the overall TCO model of the platform, but also power consumed compared to the performance capabilities. So you can see here, their existing solution, when they're doing a billion image database search, consumes 90 kilojoules of power for about 2 queries per second. And that's how they're launching this platform today. When you look at the fully optimized, as you can see the stages that we went through between using our FPGA accelerator into the ASIC-based solution and now the optimized ASIC-based solution, you can see that we're now giving them, again, significant advantages in both the queries per second and power reduction, because we're getting these into very low power ASIC-based drive solutions. So again, computational storage has significant value. You've seen multiple ways to implement it. From our perspective, we look at it from a perspective of giving both a storage device and compute resources, ultimate flexibility of those compute resources, being able to be turned on and off, and literally execute any application that you can possibly think of. The one trick is you have to compile it on ARM, and that's a very low barrier of entry for being able to deploy a significant number of accelerated core processing, especially as you start seeing the deployment of the edge market space.
Thank you, Scott. If you can give me back control. Perfect.
All yours, sir.
All right. Thank you. So the first thing we're going to do these kind of in parallel, the audience survey questions and the panel questions, just because we're a little behind. So the first audience survey question, you can answer these using your controls at the top of your screen, the Zoom controls. How familiar is your organization with computational storage? And you check one of these responses. I've just launched the poll, so you should see it up there. Just go ahead and answer. We'll give it 2 or 3 minutes to answer, and while we do that, we'll jump in and go to the first panel survey question. And this question is, what do you see as the leading use case, and I say case singular, not plural, today for computational storage? So hopefully we'll get some different views from everybody. We'll start out with Scott at NGD.
Yeah, so I had the luxury of going last and first, so it's kind of fun. From that perspective, the leading use cases today for computational storage, as you can see from everything that we're talking about, is being able to get results from data at the point of creation. From our perspective, we see that that's growing significantly as the edge platforms are being developed, and the merging of the edge data center, the edge endpoints, and the hyperscale data centers are continuing to engulf each other as we generate billions of bits of data at those endpoints into those edge data centers. Really being able to manage those large sets of data and being able to pre-screen, pre-evaluate, and use AI-based platforms is where we see the most likely use case moving forward today.
Excellent. Pankaj, what do you guys see at Samsung as the biggest use case?
We see multiple use cases. The leading one would be data analytics on very large data lakes, where standard formats such as Avro, Orc, and Parquet are taking hold. And this allows the storage to become more intelligent in looking at what is inside that data, unlike traditional block storage, which could not look inside the data, do some processing such as filtering, aggregation, some examples I talked about, and then return results to the host in such a way that the intelligent drive to the host looks just like a system. So we are seeing a miniaturization of clusters for analytics as the leading use case.
Excellent. JB, what do you guys see at ScaleFlux as the leading use case that you've seen in your deployments?
All right, well, just umbrella level, it's really any place where it's a really CPU intensive task that can consume or get bottlenecked by your Intel or AMD processor and might be better handled by a dedicated processing engine. As I showed some of the other guys showed, initial deployments have covered compression, encryption, erasure coding, inferencing, and then, but now our main focus is really on mainstream analytical databases where we look to be able to parallelize the queries across the CSDs, scaling your performance as you add storage. And again, that goes back to, as the other guys have said, reducing the amount of traffic that has to pass across the NVMe bus or the network because you're doing that processing and pre-filtering at the drive near the data.
Excellent. And Stephen, what have you guys seen at Datacom as the big use case?
So I think, the objective for any use case is twofold. One is, as JB mentioned, offloading these expensive application processors from Intel and AMD and others. And the second one is reducing data movement as we hit the I/O bottleneck that's resulting from ever-increasing speeds for storage and networking, but not the ever-increasing CPU processing capabilities that we used to be used to that aren't working anymore. In terms of actual specifics, our initial deployments are mostly around storage services. So providing, additional resources to storage capacity in the system, whether that's through data integrity or through some kind of data efficiency. But more and more, I think we're, kind of aligning to what Pankaj and Scott and JB also mentioned. Analytics on large pools of data is becoming increasingly more interesting from a use case. I think the one thing I will say is that for that to be very successful, like I said before, we need to have some kind of standardization across multiple vendors so that customers can buy product from multiple people, have a common software stack, and expect this all to interoperate. And I think that's something that's going to be very important to get, the full success of these kind of use cases.
Absolutely. Great points. All right, guys, with that, let's go ahead and launch the second survey. And all these survey results will be put on the slides. So they're sent out to you guys in a couple of days. So the second survey is, and I'm going to say this a little differently than what it says, but the real question is, for your particular organization, which of these advantages do you see as being important? So you check whichever ones apply to you. The polling's open, so go ahead and you can check those. And with that, we'll go to panel question number 2, and we'll start with Pankaj on this one. And that question is, what are the typical savings that can be realized by using computational storage for the right use cases?
So, excuse me, in our world, like when you're running single data lake that may have exabytes of data, I actually have a few customers who are starting to be 1 exabyte, and a few customers who are actually in double-digit exabytes, believe it or not, in their data lakes. What we find is that roughly 80% is row-wise data, and then 20% is columnar data, because columnar compresses well. Uncompressed, it would be more like 50-50. And the savings depend on whether you have row-wise data or column-wise data. As you all know, for columnar data, the CPU works very efficiently, and the vector processing, AVX512 and such in the CPU can be very efficient. Beating that baseline is actually quite hard. So the row-wise data, the savings start at 6x and 10x, 11x savings across broad benchmarks such as TPC-H, TPC-DS, and YCSB look within the 1-year horizon. For columnar data, where the computation is stiff, meaning the host CPU is very capable, the savings are more in the 3 to 5x range unless you apply deep semiconductor integration. Now, at Samsung, we plan to have a roadmap of greater integration, more bandwidth, and we hope to deliver 10x even on columnar someday, okay? But in the near term, we are projecting about 3 to 5x savings on columnar.
That's a big improvement, especially if you got exabytes of data. That makes a big difference. JB, what are you guys at ScaleFlux seeing as the savings your customers are realizing?
I guess the answer is always it depends here on the application and what exactly we're doing. But we've seen from the low end where 15% improvement, which with lots of data is still a very, very valuable piece, to in the over 2x, and in some cases on some TPC-H over 5x and pushing towards 10x improvements on some of those queries. And so it's the benefits are both that performance improvement, and then also on the TCO side, where like on the Hadoop example, we calculated a 30% reduction in the TCO over 3 years. I think the TCO is going to have increasing savings as we get to larger and larger data sets.
Excellent. Stephen, what are your customers saving by using your solutions?
So we did a white paper with AMD on some analysis on one of their Naples server, and we hope to bring that to Rome as well. And I think what was interesting is there's really 3 categories of savings that you can get. So I think Pankaj and JB both mentioned the offload the processor, do something more efficiently. And those numbers of 10-fold and so forth, seem pretty typical to what we've seen. Sometimes you can get more and sometimes you can get less. But the second set of savings comes from this data reduction in and of itself. So getting data off the PCIe subsystem, avoiding having to move it through system memory multiple times, that saves you a lot of energy in terms of the power consumption of the server. And it also typically means you can deploy a smaller server than you could have before. So you're saving both CapEx on your processor choices and OpEx in terms of the power consumption of those processors. And then the third saving that we've seen, and we did this again with AMD, is that because now the traffic is in the PCIe subsystem, you're not moving data back and forth to the CPU. The applications running on those processors, the databases, the virtual machines, they get much better quality of service, which means you can charge your customers more for them than your competitors can, because your customer's experience is better. And that is something that's a little harder to quantify, but we've seen massive improvements in the quality of service tail behavior of VMs running on a system that's deploying computational storage versus one that is not. And that, I think, is it's a little harder to quantify, but it's potentially one of the best benefits because it's customer visible and it's something that you can charge for.
Very good points. Scott, what about you guys at NGD? What have you talked a little bit before about, if you want to expand on that, what savings your guys are seeing?
Another thing that we're saving that's a little less conventional, a little more creative is, I would say, saving lives is another thing that you can say that computational storage is capable of doing. So what I mean by that is we have a customer that in the aerospace environment that's deploying our solution today. Their current environment, they have a canister on the plane that collects all the telematics and sensor data for the aircraft. It's a quote unquote dumb storage cartridge that's pulled out of the plane just like luggage, plugged into a server at the gate, and it takes, for a 2-hour flight, generates about 4 terabytes of data. Plug it into the server, takes about 4 hours to analyze. The plane's already back in the air. So situations like that are another way that we can look at the way that computational storage provides savings. From a more traditional IT perspective, it comes back to TCO, like everybody's talked about before. Physical space, power, And JB even mentioned the, the multi-year TCO capabilities that exist with these particular solutions. So CapEx in some cases may be higher because you're buying SSDs over hard drives, and we get that. But the overall OpEx CapEx number, we've seen as much as a 50% reduction for a given customer in operational expense, let alone the CapEx, OpEx combined delta. So kind of just echoing everybody else and throwing out that one little extra just for fun.
Excellent. And with that, let's go ahead and do the third poll question. The third poll question is, again, a multiple choice. What do you see as the greatest challenges to implementing computational storage in your organization? I will launch the polling. You should see it now on your screen. And just use your Zoom controls to answer, and then we'll share the results. And with that, we'll go to the final panel question, and that is kind of related. What do you think is necessary to overcome the ecosystem challenges that computational storage faces? And JB, we'll start with you on that one.
All right. Well, I think Scott and Stephen have actually touched on a couple of these already, which is first one is the standards-based method for identifying and communicating with computational storage devices. That's really going to be needed to overcome the hurdle of getting application developers to enable hooks to take full advantage of computational, to identify that, oh, this drive can handle my query offload for me, or handle parts of the query. And then another piece that hasn't been mentioned yet is really just the end user awareness, that the computational storage exists and what its benefits are. So I appreciate this call as a way to help expand people's understanding and knowledge of computational storage being available. And then just as a note, all the companies on this call are, along with the dozens others you showed on the SNIA slide, are working together to create those standards so that we can get rid of these hurdles and get the values of computational storage out there broadly.
Excellent. Stephen, what do you see as the biggest challenge that needs to be overcome?
Mike, I think we need three things: standards, standards, and standards. So, NVMe is the transport by which computational storage will succeed. We need, as a SNIA technical working group and as NVMe members, we need to make the technical work to update the standards to understand computation the same way NVMe understands storage. And then we need to go update operating systems, write user space libraries in a collaborative and open source fashion, and get to the point where customers can safely buy product from any of the people on today's call and know it's just going to work in their system, plugging it in, building on top of open source software, and seeing the benefits that we've described. And I think that's where we ultimately have to get to.
Yeah, that makes perfect sense. Scott, what do you think?
I have to agree with everybody else on the call being as far as what JB and Stephen have already said. Standards is a very key aspect. Again, that's why the four of us are some of the very founding members of it. From that perspective, is we being innovators in the space and first to develop solutions. It was important for us to all realize that no one of us, even some big companies, can stand alone in this space. I think another aspect of it is education, conversations like we're having today, to help people understand that this term computational storage isn't scary, and that it is something that can be deployed and developed very easily. So a lot of it has to do with education as well, which is why there's a big emphasis at SNIA, the SNIA events, even the Flash Memory Summit this year is going to have a very large footprint of computational storage, because people that are in the market get it, the people we're talking to understand it because we tell them how. The general populace, from an analyst perspective, from a press perspective, and just from the other people in the organizations that don't live and breathe storage, the education piece of it's important.
Excellent. And Pankaj, what do you guys think from Samsung? What is your view on making it more for these challenges?
I see a lot of work ahead of this industry. I agree with the co-panelists that getting the message out, showing benefits on a number of applications, putting the product in people's hands, especially software developers' hands, I see blue-collar elbow grease as the biggest challenge of computational storage. What do I mean? What I mean is that, this goes back to the comment by the moderator, which said, you have to modify applications. Well, if you look at, genomics applications or database applications or storage array software, this is not software that you can ask a generic programmer to do. This is specialist programmers. And, I'm sorry, I said blue collar. I meant white collar elbow grease. And so what I see is that, best practices, not standards, is the first priority. I view standards as a priority, but I would like to see them emerge from best practices. I think best practices in computational storage are still forming. I also see a key role for semiconductor technology, because currently the power and cost structure of these devices, when you achieve a requisite level of performance, is not satisfactory. And I see need for deeper integration that, the benefit will become more pronounced as we apply real semiconductor technology moving forward. Finally, a major vendor has to hit mass production to get to a platform that not just, storage specialists and other device companies can use, but companies like database companies, appliance companies, they can buy a product in mass quantity. Finally, let me make one more point. I mean, from having built these kind of devices over several generations at multiple companies, one of the things I realize is you start with a power-constrained device, which is flash memory, and you're trying to add a power spender to it. Without IPs that have very good QOR, I mean quality of result, you will not be able to hit performance per area that is needed to take computational storage to the next level. So I see for core areas like compression, encryption, database filtering, standard format parsing. In these areas, I see need for a new class of IPs that are more suitable for computational storage, and these are different from IPs that are happening in computational acceleration or network acceleration. Storage acceleration IPs are even more demanding, and we don't have them yet. Okay? These are some areas I see moving forward.
Right. Excellent responses. And with that, guys, let's jump into the Q&A. We have 2 questions, and we'll give everybody a chance to answer them. Let's start with the second question first, because I think it'll be a little shorter. And that question is, big organizations or IT-heavy companies will clearly be interested in these approaches. How fast will adoption spread to more mainstream organizations? Why don't we go ahead and start, JB, with you on that one?
Sure. So it really depends on the feature or the aspect of computational storage that you're looking at. So, some of the things that we talked about here were, I think Stephen talked about RocksDB. We've got a specific database as well, where those may be more niche and aimed at specific users in a small segment of the market. Then there's other features like inline data compression, decompression to give you significantly more space on your SSD that can be, you don't have to have a big IT department to deploy those and take advantage of it immediately. So I think it's really a matter of when you have a mainstream computational storage service or computational storage feature versus a niche feature, that's when it gets deployed more broadly.
Excellent. Pankaj, what do you think?
I see, 3 kind of levels of computational storage. One is, bare metal, which I expect actually even some of our colleagues to embrace, for example, a standard platform from Samsung at some point in time for volume manufacturing and semiconductor integration packaging capabilities that we can bring to the table. I see a second level of adoption where, to the bare metal platform, Samsung's adding IPs in core areas such as storage IPs or virtualization IPs. This would be for infrastructure as a service providers, which would be qualifying as mainstream, or storage array vendors, which would also qualify as mainstream, same as previous speaker. And then finally, I see, the database market, which the comment was it is niche. It's not niche. It requires framework connectors for RocksDB, for Postgres, for Spark, for many other proprietary and open databases. And I think it just takes time to develop framework connectors and optimizers. And we are at the beginning of the journey. So it will take a lot more startup companies and a lot more efforts at large companies to address the database and data analytics opportunity. So I see those, kind of a three-step path to adoption in that way, Michael.
Excellent. Scott, what do you guys think?
Yeah, I think it ties into what everybody's been talking to so far, which is just I think as these big organizations adopt and people see it, the fast follower movement comes into play. So it's just a matter of seeing more and more companies that show how easy it is, the more widespread it becomes. So, and that's back to my education concept is really where I come down to. That would add on to what everybody else has said.
Excellent. And Stephen, last to you, what do you see as the timeframes for adopting computational storage in more mainstream organizations?
Mike, I think it's all around standards, followed by software development, followed by consumability. So I think basically there's going to be a curve where as it gets easier to deploy, as these things get more consumable, more people are going to embrace them and adopt them. So I agree with Scott's point. We're going to have some early adopters who are going to be very swift to pick this up. They'll tend to have, teams of software developers who can overcome any of the kind of initial teething problems and hurdles. But there'll be a large kind of, middle of the bell curve who are going to wait to see standards in NVMe and other protocols. They're going to wait to see operating system updates. They're going to wait to see user space libraries and database tie-ins like Pankaj mentioned. So I think we'll see a lot of people, we'll see a number of people adopt quick, and then we'll just see more and more come on as more of this standardization work occurs.
And our last question is, which APIs do you use to do the offloads? And is it easy to add the storage to a custom application? Why don't we go ahead and start with Scott on that one, and we'll go through all the panelists.
I think we kind of talked through that a little bit as we went through the presentation as well. So today, a lot of it's custom per user, and so that it would depend on each vendor for the APIs that they're making available. I would say that all of our goal would be to provide APIs that make it very easy and integratable into any other type of application. In our case, it's very lightweight. We provide an API that can be integrated into any other platform. And it's keep it simple, stupid from our perspective is kind of the answer to that one.
Excellent. Stephen, what about you guys?
Well, like I said, I think NVMe is going to be the path by which we talk to these devices. So regardless of whether it's a CSP or a CSD or a CSA, we're going to be using NVMe as the protocol. I think what has to happen then is, like Pankaj said, white collar elbow grease software developers are going to have to collaborate in a vendor neutral way to develop these APIs that tie into NVMe. And then we go update open source software, one time only changes for multiple vendors to allow these applications to just almost without even thinking about it, start to take advantage of these CSPs and CSDs and so forth. And ultimately what we'd like to see is somebody just plugging one of these devices into their system, and their system just runs better. And they don't even necessarily have to touch any line of code at all. The work's already been done. It's going to take a while to get there, but that's where we hope to end up.
JB, what is your guys' position on this?
Yeah, I think agreeing with both Stephen and Scott on the futures here and the state of the union today. We do have our own custom. But we also we've done what we call turnkey application integrations, where you just install our driver and plug and play. As far as adding storage to a custom application or adding computational storage, it's certainly very easy to add the storage. It typically is plugging in directly as it would a standard SSD, and you're communicating with it just like you would with an SSD. But to take full advantage of the computational capabilities in a custom application, that's going to require currently some work with that application provider and the computational storage provider.
Excellent. And Pankaj, you're the last one to answer this one. How easy is it to add, and what sort of APIs do you guys use to do the offloads?
So I see, market-specific answer here. To some extent, in the storage services market, which is well understood application of SSDs, and then as you add compute to those SSDs for storage-oriented use cases such as compression, encryption, decryption, and deduplication and such, you can imagine what Stephen said and what the standards group has been working on together, that NVMe could evolve to carry accelerator commands. I think there is a lot of work left to do there, but I think that I agree with the co-panelists that that's a path for storage services. In the other two markets that I see, which are major markets for this, one is rich media. There I see that, the flow is more like key value. Sometimes it looks a little bit like a media object store, like a digital asset management system. Sometimes it looks like machine learning. And people are already used to using accelerators such as GPUs and FPGAs. So they're arriving at these devices, accelerator first, not storage first. They are not clamoring for NVMe to carry anything. In fact, in most cases, they don't even expose storage to the outside, okay? So what we are seeing there is that there are custom stacks which are application specific. CDNs see a very different one than streaming than others. And I don't think imposing a standard in an environment where best practices are so fragmented is going to work. So I don't think that one is going to go the NVMe route. And in fact, it wants to see the accelerator from the intelligent device as a targetable accelerator using things like Vivado or SDXL or such common accelerator-based stacks. Even multi-vendor stacks like LegUp is more desirable than, say, NVMe. Finally, in the database market, the benefit is not delivered if you only embed the compute, but then you cannot target it. So the relationship between optimizer, orchestrator, and IP is very sacred in the database world. And they've been practicing this area for 40 years. So their best practices are already well established. They're not looking for storage anything. In fact, they know how to use accelerators. They're just looking to have that accelerator close to the data and then target the memory placement of the accelerator's buffers really close to where the IOs can come. So they're just looking for co-placement. They're not looking for anything fancy. And I think this idea that one API will conquer them all is not a good idea in my opinion. That's why I say that I think the response to what APIs will there be to computational storage is going to be vertical specific. It's going to be opportunity specific in the foreseeable future.
Yeah, it certainly depends on where people are coming from, the way they look at things differently. That's very true. Well, thank you everybody for participating. As we said at the beginning, you should get the slides and a link to the recording in about 2 days. We'll send that to everybody who registered for the webinar. Thanks again to our sponsors at ScaleFlux, Samsung, NGD Systems, and Idetacom. And I hope you have a great day. Thank you very much.
Thanks, everyone.
Thank you, Mike.
Bye, everyone.
Have a great day.